You've probably boiled water 1,000 times, right? For coffee, for tea, for pasta. But have you ever really stopped to think about what's going on in that pot? It seems so simple, but it turns out there's some seriously cool and kind of weird physics happening right there on your stovetop. So let's get into it.
And yeah, I'm serious. Do we really understand it? We see it every single day. It's one of the most common things we do in the kitchen. But the actual science behind those bubbles and all that steam, it is packed with surprises that, honestly, might just flip what you thought you knew completely on its head.
All right, so first things first, let's break this whole thing down. What is actually happening in that pot of water? What does it even mean for water to boil?
Think about it. The very first thing you notice, it's always those little bubbles, isn't it? Long before you have that big rolling boil, they start showing up right at the base. So why there? Why always at the bottom?
Well, there are two big reasons for this. The first one's pretty obvious, right? The heat source is at the bottom, so naturally that's where the water heats up first. Makes perfect sense. But the second reason is the really cool part. The bottom of your pot, even if it looks perfectly smooth, is actually covered in microscopic scratches and pits. These tiny imperfections are called nucleation sites, and they are the perfect little starting points for bubbles of steam to form. And yeah, you heard that right. Those first bubbles aren't air. They're actually tiny pockets of steam.
And this brings up a really crucial distinction. Boiling is absolutely not the same thing as evaporation. Evaporation is kind of a gentle, surface-level thing, like a puddle slowly drying up on a cool day. It can happen at almost any temperature. But boiling is a whole different beast. It's a violent, energetic process that happens throughout the entire body of the liquid, and it only kicks in at a very specific temperature.
For water, at least at standard sea level pressure, where most of us live, that magic number is, of course, 100 degrees Celsius, or 212 Fahrenheit. That's the exact point where the water molecules finally have enough energy to fight back against the weight of the atmosphere pushing down on them and burst into steam. Not just at the surface, but everywhere.
But here is where it gets really weird. Once the water hits 100 degrees Celsius, it stops getting hotter. I'm serious. You can crank up the heat on your stove as high as it will go, but the temperature of the water itself will stay locked in at exactly 100 degrees. So where's all that extra energy going? It's being used for one job and one job only, breaking the bonds holding the water molecules together and turning the liquid into a gas. You're not making hotter water, you're just making steam faster.
So that 100-degree rule seems pretty simple. But, and this is a huge but, it is not a universal law of physics. There's another major player in this game, a hidden variable that can change everything. And that variable is pressure. It turns out the boiling point of water is completely dependent on the air pressure around it. Here at sea level, it's 100 degrees Celsius. But if you go hiking up a high mountain where the air is thinner and there's less pressure, water will boil at just 90 degrees. And if you take it to the extreme, in a near vacuum with almost no pressure at all, you can get water to boil at 0 degrees Celsius, the exact same temperature that it freezes. How wild is that?
Now, this isn't just a fun science fact for a trivia night. This has very real-world consequences. It explains a classic problem for anyone who's ever tried to cook up in the mountains. Why is it so incredibly hard to cook something like rice or beans at high altitudes?
Here's the catch. Your water might be bubbling away furiously, a full rolling boil, but its temperature could be only 90 or even 85 degrees Celsius. And that is simply not hot enough to properly break down the starches in the rice or soften the beans. The water boils away into steam long before the food ever gets a chance to actually cook.
So how do you solve this puzzle? Well, the solution is actually pretty elegant. If low pressure is the problem, then the answer is to create high pressure. You have to fight pressure with more pressure.
And this is the absolute genius of the pressure cooker. By sealing the lid, you trap all the steam that's produced. That trapped steam has nowhere to go, so it builds up the pressure inside the pot, way above normal atmospheric pressure. This forces the boiling point of the water to climb all the way up to 121 degrees Celsius. And at that super hot temperature, food cooks incredibly fast.
Okay, so now that we know the rules of the game, temperature and pressure, let's look at what happens when we break them. Because this is where the physics of boiling water gets truly strange and even a little bit dangerous.
So remember how we said bubbles need those little scratches, those nucleation sites to get started? Okay, but what if there aren't any? What if you heat up really pure water in a perfectly smooth container, say a brand new ceramic mug in a microwave? You can get a bizarre phenomenon called superheating. This is where the water can actually get hotter than 100 degrees Celsius without boiling at all.
It just sits there, looking perfectly calm, but it's in this highly unstable, super energized state, basically waiting for a trigger to release all that pent-up energy at once.
And that trigger can be almost anything, just bumping the cup or dropping in a tea bag or a spoonful of sugar. The second you do, the water can erupt in a violent explosion of steam. This is a very real danger, and it's why you have to be really careful when you heat water in a microwave.
And what's really interesting is that this strange phenomenon has an opposite twin, supercooling. Just like you can heat water above its boiling point without it boiling, you can also cool pure water below its freezing point of 0 degrees without it turning into ice. Both of them are these incredibly unstable states, just waiting for a nudge to snap them back to reality. So we've seen how temperature and pressure are basically the two dials that control whether water is a liquid or a gas. But what if there was one perfect, almost magical spot where solid, liquid, and gas all come together at once? You see, freezing and boiling, they aren't really separate events. They're just different points on a single continuous map that's defined entirely by those two variables, temperature and pressure. And on that map, there is one truly unique spot. It's called the triple point. It is the one single unique combination of temperature and pressure, or ice, liquid water, and water vapor can all exist at the exact same time in perfect, stable balance with each other. Now, to make this happen, the conditions have to be incredibly precise. The temperature needs to be just 1/100th of a degree above freezing, 0.01 degrees Celsius. And at the same time, you need a very specific, very low pressure, less than 1% of the normal atmosphere we experience every day. But if you can get those two conditions just right, you can watch water freeze, stay liquid, and boil, all in the same container, all at the same time.
So the next time you boil a pot of water, remember all of this. A whole universe of complex, beautiful physics is hiding right there in plain sight. And it really makes you wonder, doesn't it? What other incredible science are we completely overlooking every single day?